Today we're talking about midpoints and distances. Let's start with midpoints. Our first question is to find the midpoint of the line segment with endpoints 2, 3, and 4, 1. So here we see that line segment. And because this is such a nice little line segment, we can actually tell just from looking that the midpoint has to be right here at 3, 2. So there's our midpoint, and those are the coordinates. Now notice that 3 is the average of 2 and 4. It's the average of the x-coordinates. 2 is the average of the y-coordinates. And midpoints will always work like that. So the midpoint formula gives us that the midpoint of a line segment with endpoints x1, y1 and x2, y2, well, we want to just average the x-coordinates together and average the y-coordinates together. So that is x1 plus x2 over 2 for the x-coordinate and y1 plus y2 over 2 for the y-coordinate. So now let's take an example that we couldn't just eyeball. You can tell that the midpoint's going to need to be somewhere around here. It's not immediately obvious exactly where, or it's certainly not as easy as this one. But let's use the midpoint formula. So when we plug in our x1 of -2 and our x2 of 5, well, this is what we get. That simplifies down to -7/2 and 1/2, which we can plot on the graph right there. So now let's talk about the distance formula. We want to start again with an example where we find the distance between the points 2, 1 and 5, 6. So here's a graph with these 2 points plotted. We want the distance between them, which is the length of this line, which I can find using the Pythagorean theorem if I build a right triangle. So here's a helpful right triangle to look at. In order to use the Pythagorean theorem, which, if you remember, is a squared plus b squared equals c squared, where a and b are the lengths of the legs and c is the length of the hypotenuse, I would need the length of the legs in order to find this. Fortunately, that's easy to tell from the graph. The length of this leg is 3. The length of this leg is 5. And then I have enough to use the Pythagorean theorem. The hypotenuse has to be the square root of 3 squared plus 5 squared, which if I calculate that, I get the square root of 34. And we will always be able to build a triangle like that. But we don't have to build a triangle. We can just take a formula from that sort of setup, and we'll have the distance formula. So the distance between any points, x1, y1, and x2, y2, is given by the distance formula. It's the square root of x2 minus x1 squared plus y2 minus y1 squared. You can see how this corresponds to what we did before, because this gives you the length of the horizontal leg, this gives you the length of the vertical leg, and this formula is essentially the same as the Pythagorean theorem, giving you the length of that hypotenuse, which is the direct length between the 2 points. So let's do another example. We're going to find the length of this line, the distance between these 2 points, without drawing a triangle. We're just going to use the distance formula. So the coordinates are 3, -6 and -5, 6. So there are my 2 points. Here's my formula. x2 minus x1 squared plus y2 minus y1 squared, and then take the square root of the whole thing. When I calculate these, well, this is negative 8 squared is 64. Positive 12 squared is 144. And when I add those together, I get 208. Now, 208 is equal to 16 times 13. So, since 16 is a perfect square, I can pull out the square root of that, which is 4, and I get 4 root 13. We will want to leave our answers as exact values involving the square roots, but we'll also want to simplify them like this whenever possible. Next, let's look at this situation. We want to determine whether these points, negative 11, 1, 15, negative 2, and 0, 13, form a right triangle. So first, let's look at a graph. We can see the 3 points here. If we connect the dots, well, if it is a right triangle, then C is the right angle here. But this is not really something that I can definitively eyeball from this graph. We need a more reliable way to determine whether this is a right triangle. So we want to remember the Pythagorean theorem, and if this is a right triangle, then a squared plus b squared will be equal to c squared, where a, b, and c are these lengths that are marked on the graph. So we can use the distance formula and find the lengths, those 3 lengths. A is the side BC, and if we use the distance formula here, we'll get 15 times the square root of 2. You can redo that calculation on your own to verify that if you want. Then B is AC, and that ends up being the square root of 265. C is AB. That is the square root of 685. This is just based on the distance formula from the previous slide and the coordinates of these points. Now that I have these 3 numbers, I want to test those in that formula and see if a squared plus b squared actually is equal to c squared. So when I plug them in and square everything, I get 450 plus 265 may or may not be equal to 685. When I add those together, I get 715, which is definitely not 685. And from that, I can conclude that even though it looks like a right angle, it is definitely not a right triangle. So now we're going to talk about another situation where the distance formula comes in. Say we want to consider the set of all points that are a distance of 5 units away from the point 2, 3. I can use my set builder notation for this. And remember, the thing before the bar is what is in the set. Earlier, we always had a single variable here, maybe with some restrictions of what set it was coming from. But this is going to be a set of points, so it'll be the set of all points x, y. So x is my x-coordinate, y is my y-coordinate. And the condition for being in this set is that the distance away from the point 2, 3 is 5. So I can use the distance formula to express that this way. So this is just the distance formula with x, y, and 2, 3 being substituted in. And that distance needs to be equal to 5 units. So now I can take this condition, if I pull that out, and then maybe square both sides to get rid of that square root, I'll end up with x minus 2 squared plus y minus 3 squared is equal to 25. And that should look familiar. That form should look familiar since you have done the graphing activity before watching this video. That is a circle with a center at 2, 3 and a radius that is 5 units long. So let's say this is a good time to mention, based on that activity, you should have noticed that a circle with a radius r centered at the point h, k has the equation x minus h squared plus y minus k squared equals r squared. This is called center radius form of an equation of a circle for somewhat obvious reasons. And next you will need to watch the More About Circles video to learn some more about circles.